So ERW, enhanced rock weathering, explain it to me.
If we look back at geologic time, rock weathering has been one of the primary drivers at pulling CO2 down from the atmosphere. Basically just means when it rains on these silicate rocks, they weather, so they dissolve, generate something called alkalinity, which pulls CO2 out of the atmosphere and into the water, and that water flows down streams, rivers, into the oceans. Rock weathering over a long geologic time will help draw CO2 down, but not on speeds that are relevant to humans. And so our question is, what if we could speed that natural process up? It turns out that the simplest one might actually be the most effective. And that's to take those same rocks that we already have and just crush them up to increase their reaction surface area, and then take them and spread them in areas that are high in CO2, like cropland, to increase that reaction rate. And all of a sudden, you can go from removing carbon over, say, geologic time to really human timescales, just a couple years.
And so why cropland versus just, I build a factory where I spread this stuff out in trays, or I throw it on the desert?
We didn't want to build anything new. What are the systems that are already operating at gigaton scale? You come to two things: mining and agriculture. You have these quarries that are surrounded by farmland, and you have all of the infrastructure to already do this, the crushers, spreaders, haulers, et cetera. We found is that if we could figure out the right parameters about exactly how should we crush this rock, to what grain size, how much should we apply on any given field based on the crop type, the soil type, the rainfall, all of those things, we could start to remove carbon pretty quickly and not have to build a bunch of new infrastructure.
So one of the big challenges of this, you call it an open system approach, which just means you're doing it out in the real world, not in a confined environment that you can measure all the inputs and outputs. So the challenge is measuring what happened. How do you handle this?
That's the real crux of the company, because it seems a little bit too good to be true. You're saying we have billions of tons of this rock, millions of hectares of farmland. We don't really have to build anything. What's the catch? And one of the catches is that it's really hard to ground truth measure how much carbon is being captured. And while you can have some models today that will predict what we think should be happening, we need more evidence. And so that's what our company has been working on, is developing approaches to ground truth measure actually how much carbon is captured, and doing that today in a way that's honestly not that scalable. It's very expensive, very labor intensive, but it's building up data sets for us to empirically show that this works, be able to publish that to the world to get really momentum around this solution, and then using that data to calibrate and validate these things called reactive transport models, which are often used in nuclear waste disposal, but they need a lot of data to really be accurate. We're taking thousands of samples per field of soil core measurements. It really adds up. And then in addition to that, installing direct ways to look at treatment and a control, really showing hey, if you're saying you're capturing carbon, show me the carbon. So to do that, we're having to take a bunch of measurements. You'll see our team literally paddling down rivers with kayaks and sensors to actually take that today. And you might be wondering, okay, how is that going to scale? And that won't, but it's the first step to getting this started.
And then once you do this not particularly scalable solution, how do you turn that into something that's economically viable?
As we do this on a larger and larger area, one is our signal gets a lot stronger. So the amount of measurements that you need becomes smaller. So we have to increase the scale, we have to increase the precision, and then we ultimately have to use that data to start to calibrate some of these models so that we can make inferences onto those fields that we're not actually measuring.